Dear student, previous class I discussed about the introduction of solution, types of solution, classification of binary solution, concentration of the solutions, and finally I discussed some problem related to the concentration of the solution. Now I will discuss about the solubility of gas in liquid. That means here gas is the solute, liquid is the solvent. Suppose I will take a liquid solvent. The volume of the liquid solvent is unit. That means 1 unit.
The partial pressure of the gas which will be dissolved is 1 atm.
And the temperature is experimental condition temperature. Then what amount of gas dissolved in this liquid solvent, that is called solubility of that gas in liquid. So I can write a definition. It is defined as the volume of the gas dissolved in unit volume of liquid solvent at the temperature of the experimental condition and under a partial pressure of 1 atm of the gas to form saturated solution. Remember an important point, the solubility of the gas in liquid always expressed in absorption coefficient. Mathematically, the absorption coefficient is given by a formula. The absorption coefficient A equal to volume of gas dissolved, suppose this is taken as V, divided by volume of liquid solvent into partial pressure of the gas. Suppose volume of liquid solvent is taken as V0 and partial pressure of the gas suppose taken as P, then I can write A equal to V by V0 into P. Next I will explain about the factor. First is your nature of solute and nature of solvent. Here the solute is your gas and the solvent is your liquid. We know that there are some easily liquefiable gases are present like your NH3, Cl2, etc. These are the gases which are easily liquefiable. If you think about the solubility of these gas, then more amount of these gas are soluble in a liquid solvent like water. Water is the common solvent. Finally, we concluded that the easily liquefiable gases like NH3, Cl2, etc. are more soluble in common solvent like water. Next point is we know that polar solute dissolve in polar solvent. If you will take polar gases like HCl, SO2, then then this type of gases having more solubility in polar solvent like water. Finally, I can conclude that the polar gases like HCl, SO2 are more soluble in polar solvent like water. Next point is the ionizable gases are more soluble in water as compared to the other solvent. Suppose I will think about the ionizable gases like your HCl, NH3. These gases are more soluble in water as compared to the other solvent. So we can think that the solubility of this type of gases are more in water as compared to the other solvent. Next factor is your temperature. When we increase the temperature of a gas, then the kinetic energy of the gas goes on increases. That's why the randomness of the gases goes on increases. If you will increase the temperature of the gases, then the kinetic energy of the gases increases. That's why the solubility of the gases in a liquid solvent goes on decreases. That means with increase in the temperature, the solubility of the gases goes on decreases in a liquid solvent. That means I can write temperature is inversely proportional to the solubility of gases in liquid solvent. Next factor is your pressure. Effect of pressure can be explained by Henry's law. It is a important 2 or 3 mark question. What is Henry's law? Explain Henry's law. Suppose I will take a container. In the container, suppose I will take liquid solvent. Suppose I will take a gas. Now I will dissolve the gas in the liquid solvent. If I will apply more and more pressure on the gas, then more and more amount of gas will dissolve in the liquid solvent. As a result, the mass of gas also increases due to more amount of gas dissolved in the liquid solvent. That means the mass of the gas is direct proportional to the pressure of the gas. So I can write the definition of Henry's law like this. It is defined as, that means Henry's law defined as the mass of gas dissolved in unit volume solvent is directly proportional to the pressure of the gas in equilibrium with a solution at a given temperature. This is the statement of Henry's law. Now I will explain the Henry's law. According to this law, M proportional to P implies that I can write M is equal to K into P. Here M is the mass of the gas dissolved in unit volume solvent. So I can write here M equal to mass of gas dissolved in unit volume solvent. P is the pressure of the gas. So I can write here P is the pressure of the gas. K equal to Henry's constant. The value of Henry's constant depends upon nature of gas and and also nature of solvent and also temperature. There are also other statement of Henry's law. First statement is already given.
The other statement of Henry's law is
Mole fraction of a gas in the solution is directly proportional to the pressure of the gas in the solution.
next statement of Henry's law is
The partial pressure of the gas in vapor phase is directly proportional to the mole fraction of the gas in the solution.
next statement of Henry's law is
The solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of the liquid or solution.
the other statement of Henry's law is
The volume of gas dissolved in a liquid solvent at a given temperature is independent upon pressure. These are the other statement of Henry's law. Next I will explain about the importance of Henry's law. What are the importance of Henry's law? First is your preparation of carbonated beverage. In the preparation of carbonated beverage, generally we apply the Henry's law. What amount of gas is dissolved in the liquid solvent? Next application is your in deep sea diving. Henry's law is also applicable at high altitude. It is also applicable in the function of lungs. These are the importance of Henry's law. Next I will discuss about the condition for Henry's law. What are the conditions for Henry's law? Remember, all the gases do not obey the Henry's law. The gases which obey the following points, then such type of gases can obey the Henry's law. The following points are: number one is your the temperature of the gas is not too low. The pressure of the gas is not too high. The gas is not highly soluble and does not chemically combine with a solvent. Next point is the gas does not dissociate. These are the conditions for a gas which can obey the Henry's law. Next I will explain about the solid solution. If two or more solids are mixed with each other to form a mixture, that mixture must be homogeneous, then that homogeneous mixture is called solid solution. That means I can write if two or more solids are mixed with each other to form a homogeneous mixture, then that mixture is called solid solution. Solid solution are two types. One is your substitutional solid solution. Second is your interstitial solid solution. Suppose these are the solvent molecule present in a system. Suppose I will add the solid molecule in the solvent. Suppose the solute molecule substituted the solvent molecule like this.
This is your solute molecule. This is also solute molecule. The solute molecules are arranged like this. This is your also solute molecule. Here the solute molecules and solvent molecules are arranged in a orderly manner, and the
Solvent molecule.
are substituted by the solute molecule.
Here this is your solvent molecules. This is your said to be solute molecules. Look at that. Here the solute molecule substitute the solvent molecule, and the solute and solvent molecule are arranged in a orderly manner. So this is said to be an ordered substitutional solid solution. Suppose the solute molecule are not arranged in an orderly manner, then that type of substitutional solid are considered as randomly substitutional solid solution. That means the solute molecules are present in a random manner like this. Look at that. The solute molecule are not arranged in a orderly manner. So this is said to be a randomly substitutional solid solution. This is said to be your ordered substitutional solid solution. Look at that. This position is called the interstitial position. If a solute molecule present here, that means the solute molecule present like this, then such type of solid solution are called interstitial solid solution. These two are said to be substitutional solid solution. This is also said to be interstitial solid solution. The example of substitutional solid solution are alloys like brass, bronze, like this. The examples of interstitial solid solution are tungsten carbide. The other example is carbon present in the interstitial position of the iron atom in the steel. These are all about the solid solution. Next I will explain about the ideal solution and another is your non-ideal solution. Suppose I will take a solution. Suppose the change in volume, that is del V mixing of the solution is equal to 0 or nearly equal to 0, and also the change in enthalpy of the solution, that is del H mixing is equal to 0 or nearly equal to 0, then that solution is called ideal solution. If the del V mixing and del H mixing of the solution not equal to 0, then that solution is called non-ideal solution. That means in ideal solution, del H mixing equal to 0 and del V mixing also equal to 0. In case of non-ideal solution, del H mixing not equal to 0, del V mixing also not equal to 0. Example of ideal solution is your solution of chlorobenzene and bromobenzene. Next example is your solution of ethyl bromide and ethyl iodide. The example of non-ideal solution is your solution of acetone and benzene. Second example is your solution of chloroform and diethyl ether. Next point is the molecular interaction. In ideal solution is similar to the pure component. But in case of non-ideal solution, the molecular interaction are not similar with the pure component. Here, Roults law obey, here Roults law do not obey. These are the difference between ideal solution and non-ideal solution. Next I will explain about the types of non-ideal solution. There are two types of non-ideal solution. Number one is your non-ideal solution showing positive deviation. Number two is your non-ideal solution showing negative deviation. At first I will discuss about the non-ideal solution showing positive deviation. If the intermolecular interaction decreases on mixing two liquids, then that type of non-ideal solution are considered as non-ideal solution showing positive deviation. Due to decrease in the intermolecular interaction, there is a increase in the vapor pressure of the non-ideal solution as compared to the
vapor pressure of
expected ideal solution. As a result, I can write P1 greater than P10 x1. Like that, I can also write P2 greater than P20 x2. That's why I can write P equal to P1 plus P2 greater than P10 x1 plus P20 x2. There are many examples of non-ideal solutions showing positive deviation. Number one is your methyl alcohol plus water. Number two is your acetone plus benzene. Number three is your acetone plus ethyl alcohol. Number four is your acetone plus carbon tetrachloride. Next is your carbon tetrachloride plus chloroform. These are the examples of non-ideal solution showing positive deviation. Next I will discuss about the non-ideal solution showing negative deviation. If the intermolecular interaction increases on mixing two liquid, then such type of non-ideal solution are considered as non-ideal solution showing negative deviation. In this type of non-ideal solution, the vapor pressure become lesser than the corresponding vapor pressure expected from ideal solution. In this type of solution, I can write P1 less than P10 x1. Similarly, I can write P2 less than P20 x2. And also I can write P equal to P1 plus P2 less than P10 x1 plus P20 x2. There are many examples of non-ideal solutions showing negative deviation. Number one is your chloroform plus diethyl ether. Number two is your acetone plus aniline. Number three is your benzene plus chloroform. Number four is your chloroform plus acetone. Number fifth is your nitric acid plus water. Number sixth is your chloroform plus nitric acid. These are the examples of non-ideal solution showing negative deviation. Next I will discuss about the Roults law. It is a very important 3-mark question. There are two laws related to the Roults law. First is your Roults law for a solution containing non-volatile solute. Second is your Roults law for the solution containing volatile solute. At first I will discuss about the Roults law for a solution containing non-volatile solute. Suppose I will take a solution. These are the non-volatile solute. Suppose I will think about the vapor pressure of the solution. The vapor pressure of the solution completely depend upon the solvent. The vapor pressure of the solution do not depend upon the solute because the solute molecules are non-volatile. That means if I will increase the number of solvent molecule, then the vapor pressure increases. From this data I can write the statement of Roults law for the solution containing non-volatile. The vapor pressure of the solvent over a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent at a particular temperature. Look at that, if the number of solvent molecule increases, then the vapor pressure also increases. If the number of solvent molecule increases, then the mole fraction of that solvent molecule also increases. So here I can write vapor pressure directly proportional to the mole fraction of the solvent. Now I will explain the Roults law for a solution containing non-volatile solute. According to this law, if Ps equal to vapor pressure of the solvent over solution containing non-volatile solute, x1 equal to mole fraction of solvent, then according to this law Ps proportional to x1. That means I can write Ps equal to P0 x1. Here P0 equal to vapor pressure of pure solvent, vapor pressure of pure solvent. That means I can write Ps by P0 equal to x1. Now I can write 1 minus Ps by P0 equal to 1 minus x1.
Implies that P0 minus Ps divided by P0 equal to x2.
Here x2 equal to mole fraction of solute. Look at that, here P0 greater than Ps because P0 related to the vapor pressure of the pure solvent and Ps related to the vapor pressure of the solvent over the solution containing non-volatile solute. That means I can write P0 minus Ps equal to lowering in vapor pressure. For P0, the lowering in vapor pressure is P0 minus Ps. So I can write P0 minus Ps divided by P0 equal to relative lowering in vapor pressure. That means this term is called relative lowering vapor pressure. So I can write another statement for Roults law for a solution containing non-volatile solute. The other statement is the relative lowering in vapor pressure of a solution containing non-volatile solute is equal to the mole fraction of the solute. Next I will explain about the other Roults law, that is Roults law. For a solution containing volatile solute. Suppose I will take a solution. In this solution, suppose these are the volatile solute. In this case, the vapor pressure depends upon both solute and solvent. Keeping this concept, I can write the statement for this law. At a given temperature, for a solution of volatile liquid, the partial pressure of each component is equal to the product of the vapor pressure of the pure component and its mole fraction. This is the statement for Roults law for a solution containing volatile solute. Next I will explain the explanation for this law. Mathematically, I can write P1 equal to P10 x1. Another is your P2 equal to P20 x2. This is your 1, this is your 2. Here P1 and P2 are the vapor pressure of the two liquid component 1 and 2 respectively. Here P10, P20 are the vapor pressure of pure liquid component 1 and 2
respectively.
X1 and X2 are the mole fraction of component 1 and 2 respectively. According to Dalton's partial pressure, I can write P equal to P1 plus P2. Here P is the total pressure.
Now I can write
Equal to P10 x1 plus P20 x2. Next I can write P equal to P10 into 1 minus x2 plus P20 x2, because we know that x1 plus x2 equal to 1. Next I can write P equal to P10 minus P10 x2 plus P20 x2. Next I can write P equal to P10 minus x2 whole into P10 minus P20. Now I can write x2 into P10 minus P20 equal to P10 minus P. Simply that x2 equal to P10 minus P divided by P10 minus P20. Next I will explain about the limitation of Roults law. First point is if the solution is not very dilute, then there is a strong interaction between the solute and the solvent molecule. This leads to the positive or negative deviation. Second is if the solute undergoes dissociation in the solution, then there is an increase in the number of particles in the solution and Roults law is not obeyed. Third is if the solute undergoes association in the solution, then there is a decrease in the number of particles in the solution and Roults law is not also obeyed. These are the limitations of Roults law. Next I will explain about the colligative property. There are many properties of the solution which only depends upon the number of solute particles but do not depend upon the nature of the solute particle. These properties are called colligative properties. There are mainly four types of colligative property. One is your relative lowering in vapor pressure. Second is your elevation in boiling point. Third is your depression of freezing point, and fourth is your osmotic pressure. At first I will explain about the relative lowering in vapor pressure. Suppose I will take a solvent. When I will add the non-volatile solute to this solvent, then the vapor pressure of the solution become lesser than the vapor pressure of the solvent. This lowering in vapor pressure is called relative lowering in vapor pressure. If Ps equal to vapor pressure of the solution containing non-volatile solute and P0 equal to vapor pressure of the pure solvent, then P0 minus Ps equal to lowering in vapor pressure, and I can also write P0 minus Ps divided by P0 equal to relative lowering in vapor pressure. According to Roults law, I can write P0 minus Ps divided by P0 equal to x2. We know that x2 equal to n2 by n1 plus n2. Here x2 is the mole fraction of the solute. Here n1 is the number of mole of solvent. n2 is the number of mole of solute. So we can write del P by P0 equal to n2 by n1 plus n2. Here del P equal to P0 minus Ps. Look at that. Here relative lowering in vapor pressure depends upon the number of solute present in a definite number of solvent in a solution. So relative lowering in vapor pressure is a colligative property. A question always asks, prove that relative lowering in vapor pressure is a colligative property. Next I will explain about the determination of molecular mass from RLVP. RLVP means relative lowering in vapor pressure. According to Roults law, I can write P0 minus Ps divided by P0 equal to x2. Imply that I can write P0 minus Ps divided by P0 equal to n2 by n1 plus n2. For a very dilute solution, we know that the number of mole of solute is very less than the number of mole of solvent. So we can write for a very dilute solution, n1 is much more greater than n2. So here I can neglect the n2 value and only I can write n1. That means I can write P0 minus Ps divided by P0 equal to n2 by n1. Here n2 is neglected because very small value as compared to the n1. That means I can write n1 plus n2 nearly equal to n1. We know that number of mole equal to weight of the substance divided by molecular mass. So I can write P0 minus Ps divided by P0 equal to W2 divided by M2 divided by W1 by M1. Here W1 is the weight of solvent, W2 is the weight of solute, M1 is the molecular mass of the solvent, M2 is the molecular mass of solute. Next I can write P0 minus Ps divided by P0 equal to W2 M1 divided by W1 into M2. Now I will solve a problem related to the relative lowering in vapor pressure. This is the problem. The vapor pressure of water at 298 Kelvin is 17.5 mm Hg and lowering of vapor pressure of a sugar solution is 0.061 mm Hg. Calculate the relative lowering of vapor pressure. Here P0 minus Ps equal to 0.61 mm Hg. P0 equal to 17.5 mm Hg. We know that relative lowering vapor pressure equal to P0 minus Ps divided by P0. That means I can write 0.61 divided by 17.5 equal to 0.0035 mm Hg. This is your answer. In this question, you are aim to find out the relative lowering of vapor pressure. So I can write the relative lowering of vapor pressure equal to 0.0035 mm Hg. This is all about the relative lowering in vapor pressure and its problem.